Let us look at another 1-pulse diode rectifier circuit or single phase half-wave rectifier. Here in the power electronic converter we have an inductor in addition to the diode D1. Resistor is the load and Vs is the voltage source, which is sinusoidal. Let us go by the same method. Prior to t equal to 0, there is no current in the circuit, and then at t equal to 0, the source voltage goes positive and it stays positive between 0 and pi. And let us say we assume that the diode is off in the positive half cycle of input voltage. So since we have assumed that the diode is off, we have to make sure that the voltage across the diode is negative. So as we assumed that the diode is off, the current ID1 is 0. So we need to look at VD1, and VD1 is Vs minus Vo dash, shown here, and Vo dash is equal to 0 because there is no current flowing in the circuit. So VD1 will be equal to Vs, which is actually greater than 0. So we are inconsistent with the assumption. So D1 should be on when Vs is greater than 0. And in that case, what will be Vo dash? Vo dash is equal to Vs, since the voltage across the diode is almost 0 when it is on. And how does the source current look like, or the diode current look like in this interval? We have to solve a differential equation for that. And what is that differential equation? Basically what we obtain from the KVL equation. Vm sin omega t is equal to R times Is plus L d by dt of Is. This will give us the shape of current waveform, and that is what is shown here in green color. And what is the output voltage? The output voltage Vo is equal to the current through the resistor multiplied by the value of resistance, and the current through the resistor is same as the source current. So IR or I output current is same as source current, and Vo in this case is simply IO times R or Is times R. What happens at omega t equal to pi? The source voltage Vs becomes negative. So when Vs becomes negative, let us assume that D1 continues to be on like we did before. So if D1 continues to be on, we need to make sure that the current through the diode is positive, because the diode cannot carry negative current. So that is the inference from the assumed state is shown in green color here. Since we have assumed the diode is on, VD1 is of course 0. We need to look at current, and the current we told earlier that it is the solution of a differential equation, and I am giving the solution of a differential equation here, which is again a well-known expression. It is ID1 is given by Vm by Z sin omega t minus phi plus A e power minus RT by L. That is the solution of the differential equation. And what is Z? Z is the impedance, R square plus omega L square under square root, and phi is tan inverse omega L by R. So if we have the initial condition that at t equal to 0 there is no current in the circuit, we can get the value of A as Vm by Z sin phi. So since the current through the diode is given by this particular expression, if this current is positive, then our assumption is correct. Our assumption of diode conducting even in the negative half cycle is correct. So D1 is on as long as ID1 is greater than 0, even in the negative half cycle, even when Vs is less than 0. But when will it turn off? From the expression of diode current, we can say that the diode current will have a peak just after the voltage peak in the positive half, and then the diode current starts falling in the positive half itself, but it is still positive at omega t equal to pi. That is why the diode continues to conduct. And when will it stop conducting? It will stop conducting as soon as this current reaches 0. And that instant, if we assume that it is omega t plus beta, it can be obtained by the solution of ID1 of t is equal to 0. You equate this solution to 0 to get the value of beta. What is the average output voltage in this case? VO average is equal to VO dash average. And why is that? Because the average voltage across an inductor is 0 in periodic steady state. That is what is shown here. You have two areas. The area under the positive part of the inductor voltage is A1, and the second area A2 is the area under the negative part of the voltage waveform VL. These two areas will be equal in periodic steady state, and that is why VO average is equal to VO dash average. And how do we get the expression for this average output voltage? Using this integral 1 by 2 pi integral 0 to pi plus beta Vm sin omega t d omega t, and that will give us an expression Vm by 2 pi into 1 plus cos beta. And what is the source current when the diode is off? When the diode is off, of course the source current is 0. That is what is shown here. From pi plus beta, from the interval pi plus beta to 2 pi, the source current is 0, the diode current is 0. So the average source current is again VO average by R, which is shown here in green dotted line. And the same waveforms continue starting from 2 pi, which is the second cycle, and it will go on. What is the voltage across the diode? How does it look like? It is shown in purple color waveform here. The voltage across the diode is 0 when it is on, so almost 0, and it becomes equal to the source voltage when it is off, Vs. So that is from pi plus beta to 2 pi. So the maximum value of voltage to be blocked by the diode when it is off is again minus Vm in this case. As you increase the value of L, as the value of L is increased, beta will increase. The interval for which diode conducts will increase, and subsequently the average output voltage decreases. Why? Because the negative excursion in VO dash is now increased. This is a negative excursion that has increased. So the average value of output voltage is decreased. So that is shown here, and consequently the average current will also be less. So an example is shown here where the value of L is doubled, which resulted in a lower value of output voltage and a lower value of output average current. The negative excursions in VO dash can be limited to 0 by inserting another diode in this circuit, where you have two diodes and one inductor in the power electronic converter that is shown here. And there are four possible states. In this case, both diodes can be on, either of them can be on, or both diodes can be off. So when Vs is greater than 0, when the source voltage is greater than 0, let us assume that both are on. Since both are on, if we apply KCL in this circuit, at this node, basically at this node, KCL is applied at this node, ID1 plus ID2 is equal to IL, and ID1 ID2 have to be greater than 0, greater than or equal to 0, because we have assumed that they are on and they cannot be negative in any way. So ID1 plus ID2 should be greater than or equal to 0. That means the current in inductor IL, or the current through the load, should be greater than or equal to 0. This is true for any case. And what is VD2? The voltage across the diode. VD2 has to be 0 since we have assumed the diode D2 to be on. But we have also assumed that the diode D1 is on. So VD1 is equal to 0. That when VD1 is equal to 0, VD2 will become minus Vs from KVL in this particular loop. So we contradict our assumption. Since we assume that D2 is on, the voltage across diode has to be 0, but it is turning out to be negative because of the assumption of the other diode being on. So the conclusion is D1 and D2 cannot be on together. By the same arguments, it can be shown that this condition is true even for Vs less than 0. So this particular state of both being on is invalid at any point in the circuit, at any instant of time. Now, how do we know which is the valid state among the other three? Let us assume one state. Vs is greater than 0, and let us assume that D1 is off and D2 is on. Since D1 is off, ID1 is 0, and since D2 is on, VD2 is 0. So since we have assumed that the diode is off, the diode D1 is off, we need to look at the voltage across it and make sure that it is negative. So if you look at VD1, VD1 is equal to Vs, again by the KVL in the loop, because D2 is conducting. So Vs is greater than 0, and we again contradict our assumption, or we are inconsistent with the property of the diode. So Vs is greater than 0. When the voltage is positive, input voltage is positive, D1 is on and D2 has to be off if IL is greater than 0. As long as the current through the inductor IL is positive, it can only be positive or 0. So when the current is positive, D1 should be on and D2 should be off, and if the current is 0, both should be off. That is the only possible case. Similarly, when the input voltage is less than 0, D1 will be off, D2 is on if IL is positive. If some current is flowing, that has to flow through this diode D2 in the negative half cycle. Otherwise, if the current flowing through inductor is 0, no device will conduct, no switch will conduct. So let us look at the voltage waveforms. When Vs is greater than 0, we know that VO dash is equal to Vs. And what is output voltage? It is again IL times R. And what is the diode current? ID1, which is equal to the source current and also the load current or inductor current in the positive half cycle. It is the solution of this particular differential equation. Vm sin omega t is equal to RIL plus LdIL by dt. And when the input voltage is negative, Vs is less than 0, VO dash is equal to 0. Why? Because D2 is on. VO dash is nothing but the inverse of the voltage across D2. And what is output voltage? It is again IL times R, but now IL is the solution of 0 is equal to RIL plus LdIL by dt. That is the KVL in the second loop, right side loop. And the source current IS is equal to ID1, which is equal to 0. So that is what is shown here. So in the first half, like 0 to pi, from 0 to pi, the current is a sinusoidal plus exponential as shown by the solution that we have written earlier. And in the second half, like pi to 2 pi, the current is a pure exponential fall because it is a solution of this particular differential equation. And the source current and inductor current overlap. Source current and inductor current overlap in the first interval, the positive half cycle, and the source current is 0 in the negative half, whereas the inductor current continues to follow an exponential function and it will come down to 0 depending on the time constant, L by R time constant. And what is the average output voltage, VO average? It is same as VO dash average, and that is nothing but Vm by pi, and that can be obtained by this integral as we have done earlier. Now what happens if you increase the value of L? If you increase the value of L, the peak to peak excursions the peak to peak excursions in current will reduce. So the peak to peak voltage ripple also reduces across the resistor. But the average voltage doesn't change. The average voltage remains Vm by pi because Vo dash is not changing. It is still that sine waveform and 0, sine value for 0 to pi and 0 for pi to 2 pi. So Vo dash remains the same even if you change the value of L. So Vo dash average will remain the same. So the average output voltage remains the same and the average output current remains the same. It is just that the peak to peak ripple in the output current is reduced. The peak to peak ripple in inductor current is reduced, and the average output current is given by Vo average by R as shown in the dotted pink line here. And if we observe, in the first half, diode D1 is carrying current IL, load current, and in the second half, diode D2 is carrying the load current IL. The diode D2 is known as freewheeling diode. Why? Freewheel is an automotive transmission device. It's a device in automotive transmission that disengages the drive shaft from the driven shaft when the driven shaft rotates faster than the drive shaft. And what is D2 doing here? D2 is disengaging or disconnecting the source from load when the source voltage is becoming negative. So that is why it is known as freewheeling diode. It is taking up the current from D1 at omega t equal to pi.